We want to deploy a modern Java application across both Kubernetes clusters and traditional on-premise environments, and we want to control it all using GitOps. At enterprise scale, this creates friction. You have massive compiled binary artifacts that must move in tandem with delicate environment-specific configurations. The most common approach is to keep everything in one place, storing the Java source code and the environment deployment manifests inside the same Git repository. This setup challenges the 12-factor app methodology, which requires building exactly one immutable Docker image per release and promoting that identical image through QA, UAT, and production. This is standard monorepo architecture. A Java application folder containing source code sits right next to a deployment folder with production manifests. On the main branch, developers are pushing new features, updating the Java code for version 1.4. However, the deployment folder must stay locked to the live servers. While the code is version 1.4, these configuration files hold database credentials for version 1.1. This creates a version mismatch within the same commit history. GitOps requires a repository to be a single source of truth, but here the repository is simultaneously representing the future state of the code and the current state of the infrastructure. This forces a conflict between developer velocity and operational stability. Developers need to iterate quickly, while operators need a space of absolute deterministic control. When configuration files and application code share the same pipeline, a change to one often triggers an unnecessary cycle for the other. To solve this, the architecture must be split into two separate systems. To resolve the friction of the monorepo, we use a two-repo strategy. Repo A is the application repository, building the artifact. When code merges, the CI pipeline compiles the Java app, builds the Docker image, and pushes it to JFrog Artifactory. It contains no environment information. Once in the registry, Repo A's job is done. Repo B is the GitOps deployment repository. It contains no Java code, only deployment manifests in environment-specific directories on one main branch. In EKS, Argo CD acts as the sync engine. It monitors Repo B's production folder, automatically applying configurations to the Kubernetes cluster. For on-premise servers running Docker Compose, we need an alternative to Argo CD to handle the sync. A GitHub action mirrors this GitOps behavior. When Repo B updates, it triggers a secure copy of Docker Compose and environment files to the on-premise server. Then, via SSH, it runs Docker Compose pull, grabbing the latest JFrog image and restarting the containers. This separation changes the operational logic of the entire pipeline. If you need to change a database timeout in production, you update the text file in Repo B. The change syncs to the cluster immediately without triggering a 15-minute Maven build. Repo A becomes the source of truth for the code, while Repo B becomes the source of truth for the environment state. Even with two repositories, the way you structure the GitOps repo determines the long-term stability of the environment. Developers often try to map Git branches directly to environments, creating separate dev, QA, and production branches. This forces reliance on Git merges to move code. Because QA and production require different settings, these branches naturally diverge. During a merge from QA to production, you risk conflicts, like a mock QA database URL attempting to overwrite the live production connection string. This makes promotion via merging unreliable, as environment-specific variables are difficult to manage using standard Git merge logic. When merges become too difficult, engineers often stop performing them, leading to configuration drift. Eventually, the QA environment no longer reflects the reality of production. To prevent drift, we use a directory per environment model on a single branch. By putting all environments in folders on the same branch, the main branch provides a real-time snapshot of the entire infrastructure. This changes how we promote a release from QA to production. Instead of merging branches, we use a pull request that copies the updated configuration values from the QA folder into the production folder. Mapping environments to branches creates divergent states that are difficult to reconcile. By using directories on a single branch, the repository remains a unified, traceable record of every environment. Without release branches in Repo B, we need a reliable way to link our deployment configurations to the correct images in the registry. In a GitOps workflow, the configuration must explicitly declare the exact version of the binary it requires. This image tag is the hard link between our state repository and the artifact stored in JFrog. This explicit link is what makes production rollbacks predictable. If a deployment fails, manual changes to the cluster are temporary. Argo CD will detect any manual intervention and immediately overwrite it to match the state defined in get. To roll back, you must roll back get. Executing a git revert on repo B changes the image tag back to stable version 1.1. When this reaches main, Argo CD commands Kubernetes to spin down failing pods and restore the previous version. For critical outages, Argo CD provides a panic button in the UI for an immediate rollback. The panic button creates drift between the cluster and Git to save time. Once the system is stable, you still need to perform a git revert to bring the repository back in sync with the live state. When managing dozens of configuration files across multiple clusters, we need a way to snapshot the state of the entire system. We achieve this by using environment prefixed tags on the main branch, such as prod v1.20. This allows engineers to perform a batch diff between two tags, showing every configuration change and image update that occurred between any two production releases. The two-repo design separates developer workflow from infrastructure state. It allows for rapid code iteration in repo A, while maintaining a clear, auditable history of environmental changes in repo B.